share, share my research with Alexis Virelizier. Yeah, this is a joint work with Alexis Virelizier. He is based also at University of Delhi, and the paper is not out yet at the moment, but we will hopefully put it out soon. So I will talk about Kuperberg-type invariants of maps from 3 manifolds to homotopy 2 types. So the title is long. Let me explain from what we know in three-dimensional topology and TQFT history. Let's recall the digraphiton invariants, which are famous in low-dimensional topology. And what is the input of a digraphiton to construct a digraphiton invariance? The input is finite group and 3 cocycle, and which is in fact a normalized, or maybe not normalized, which is in fact given as a map, just a set map from G cross G cross G to C star, and then it needs to satisfy this equation, which is the big cohomology class. And output is an invariant of close connected oriented three-manifold. So in particular, for example, this can be also trivial map. That's also possible. That means G for any GHK is just one.
Is this group abelian?
No, it doesn't have to be abelian. Not necessarily abelian. Okay. So the output is an invariant of close connected oriented three manifold. M. So let's recall how this invariant is constructed. What is the construction? How does it the step of construction goes? So, well, there are alternative approaches, but I will start with the motivation that our work is. I will start with the state sum model. Like this model can be derived as a state sum. So what we do, we choose a base point in this connected close-oriented three manifold M, and we choose a triangulation of M. So every such manifold can be triangulable, such that this chosen base point is one of the vertices. Like in here, we have triangulation, tetrahedrous, and then their faces. And we choose a total order on the set of vertices. So we put kind of numbers ordered, either numbers or some elements of the totally ordered set on the just vertices, right? And one of the vertices, remember, is M, overall, one of them. And we define a G coloring, okay? The input was this finite group G. So the G coloring of the triangulation is the following, is a map from like G to triangles. In fact, G is G cross G, maybe. In the way that it is compatible with the order of the vertices. If the label of between these two vertices is G and this one is H, then this one need to be GH. And when we do this from tetrahedrons, for each triangle, when we do this, each tetrahedra has 4 faces. There are 4 triangles. So what do we get? We in fact get like triple. In this case, it's going to be K. If you look at this, K, G, K, G, and then in this case G, H, and GH, and this needs to be KGH. So tetrahedra is like corresponds to this letter in this product in the finite group. So this is a coloring. Coloring is a compatibility assignment of G elements of G to edges of triangles that are compatible with the total order on the vertices. Okay, and the next thing is what we do, we assign a weight to, after we do for each coloring, so there is not a single coloring, there are many colors, but for each G color, we fix a G color, we define G color, and then we assign a weight to each tetrahedra. And this weight is precisely the value of this cocycle, or inverted, or itself. The value of the cocycle at the associated, remember, to this tetrahedra, we associated this triple, right? Or maybe instead of their multiplication, I better say a triple we assign G3. So we take this triple, so we evaluate this 3 cocycle that we picked at the beginning. And so we get a number in C, and we take its inverse or leave it same depending on the compatibility of the orientation of triangle with the 3 manifold. So this order on the faces induces an orientation of this tetrahedra. If this orientation is compatible with the orientation of them, then we take +1. So we leave it the value as it is. If the orientation induced by the order of vertices is the opposite of the orientation of the underlying manifold, then we take the inverse of it. So for each tetrahedra, we do this. There are only finite many tetrahedras. And then we multiply these weights as the next step over all tetrahedrons. So for each tetrahedra, we assign a weight, and this weight is an element of complex numbers. And there are finite many tetrahedra, we multiply these complex numbers. And for each G coloring, we get a number. We get this number. And we sum, the next step is for each G coloring, we do this multiplication, assigning weights, and then multiplication, and then sum overall these states, the weights assigned to states. So you may ask, okay, the number of tetrahedras is finite because I said, what do we have? M is closed, connected, oriented tree manifold. The fact that it's closed, number of tetrahedras is finite, so this product is finite. That's okay. And G colorings is finite. You may ask, where do we know? Because G is finite. And number of edges is finite. So set of possible G coloring is definitely finite because set of maps from G squares to triangles is finite. And we normalize by 1 over G to the order of G to the. So this is how do we construct the digraph with an invariant.
Excuse me. Can you explain the motivation of the omega, who satisfy the long formulation that all of the product equals 1? Can you give the motivation?
Oh yes, this is, you can think of this as okay, you can think of this as this is a base at the base point, and we have M to B G M. That's actually one of the following things I'm going to say. You consider the classifying space of this group as the TW complex, the KG1 space, and you pick a base point, and then for each labeling is indeed corresponds to a pointed map. Consider this as like sending like a map, sending edges, sending vertices of T to so sending vertices of T to X, base point of classifying space. Then when you pick such a map, it gives a G coloring. Okay, and then so this goes to a loop. This goes to a loop in in BG. So that loop is in pi1, and pi1 of this space is G. So this is labeling of the thing. So this triangle bounds, that precisely means if you go along this disk on the boundary of this thing, you need to get GH inverse 1. That is one of the motivations you can think of. So this circle bounds a disk. That's why when you go around at the boundary of this disk, it needs the pi1 element should be trivial. And in fact, it's a good question. So this invariant can be formulated as number of homotopy, like for overall base homotopy classes from M with the base point M to a classifying space of this finite group and the base point X. And what do we do? Remember, omega is a third homology class of BGC star. This is equal to H3. Well, it's class, it's a cycle, or this is G C star, right? And F is a map from M, it's a homotopy class, but choose a representative. So there's a cohomology class in here. We can pull it back to here and then evaluate the fundamental class, which is again an element in C star. Okay, and sum of overall this evaluation of the third three cocycles over the fundamental class of the manifold divided normalized this way, this equals again the same invariant. It's another approach. Think of this. Okay. So next thing is what I work on from this point of view. Like this diagram within invariance in fact leads to what is known as TQFTs, topological quantum field theories. So this is what do I mean by that? For any closed oriented tree manifold, okay, we get number, or more precisely numerical invariant. And see, but this number of this invariant can be, the question is, can be extended to surfaces, and in a way that when we glue manifolds, they behave nicely. And in the case of digraphic case, it happens, and when this happens, we call it a TQFT. So I will talk about homotopy quantum field theories, which are certain generalizations of them. So let's denote this invariant. Okay, I denote it like this, digraphic M and omega. Oh, there's a typo here. Maybe digraphic G, it's better, it's the better symbol, the inputs. So also before passing to that, so this is an invariant. What does that mean? This is an invariant of three manifold means it is an independent of the total order chosen. It's an independent of the triangulation chosen. So it's independent of also as well base point chosen. So all of the choices it's independent of. So digraphic invariant is an invariant of manifold. So this actually what is an output of an TQFT. And then if you rewrite this formula, like if you rewrite this, the second approach as an expanded, like assume there are finite dimension, there's always finite dimension homotopy class. Let's say there are K of them. And then that means this formula can be extended as like this, pulling back over all these finite dimension homotopy classes, this cohomology class, and then evaluate the fundamental class, and then sum and divide by the order of G. So this is exactly what we have seen. So the question for HQFTs, or the appropriate question, is to ask, can we get these individual numbers? Okay. So can we get these individual numbers as invariant of some, maybe instead of right, as an invariant of the homotopy class. Okay. So TQFT produces an invariant of manifold, but for each homotopy class, M to BG, can we associate an invariant like digraphic, for example, digraphic GM omega can one get invariant of this homotopy class? Not only the manifold, but also the homotopy class. And the answer is yes, and this is the content of homotopy quantum field theories, in fact. So, like, I didn't define you what is an HQFT. I will define soon. But output of an HQFT is an invariant of homotopy classes of maps. Okay, and this target in this case is fixed. And one can, this is not only possible target for an HQFT, this is a fixed target. One can indeed, to define an HQFT, one can choose any connected CW complex. It doesn't have to be KG1 or something else. One can consider a priori in general arbitrary targets. Okay, let's define what is a HQFT. When we fix connected pointed CW complex X, a three-dimensional homotopy quantum field theory with target X is a symmetric monoidal functor from this cobordism category to the category of finite dimensional complex vector spaces. So, question is, what is this cobordism category, which is defined using this target? Okay. Remember, maybe first, COB3. COB3 is objects are oriented closed surfaces. And morphisms, oriented cobordisms. Up to diffeomorphism relative to the boundary. So this is the usual cobordism category, three-dimensional cobordism category. And then we put this extra X that is precisely equipping these elements with maps to this space. Okay. Both morphisms and cobordism are going to be equipped with the maps to cobordism. So think of, for example, in this case, think of this handle body. This is the genus 2 handle body. It's a compact three-dimensional oriented manifold, and remove a disk inside, 3-disk. This is a 3-disk. When you remove, so its boundary is going to be this S2, sigma 1, addition union with the sigma 2. So this is a cobordism from sphere to genus 2 surface, a three-dimensional cobordism, oriented cobordism. But this is an element, this itself is an element of, in fact, COB3. But to be element of a morphism of X COB3, we equip these things with homotopy class of maps. So we equip, well, in fact, a continuous map on the boundaries. On the boundary surface 1, it has a map from sigma 1 to X, which takes the base point of the boundary to the base point of this. And on the other boundary, we have sigma 2, it's a genus 2 surface. It has a base point, and we equip it as a continuous map, which takes this base point to X. And on the whole cobordism three-dimensional piece, we equip it with a homotopy class of map, which extend these two. So the point is, we have before oriented surfaces and oriented cobordisms. For X cobordism category, that is fixed target space X, we have additional, for each such element of the cobordism, we have additional pointed maps, pointed oriented surface, and a pointed continuous map to the fixed target. And similarly, for the cobordisms, we have homotopy class extending this pointed maps. So this is one observation one can make. This category is way larger than the cobordism category. And so what is then okay, this is the cobordism category that I defined. We just add this pointed continuous maps on the boundaries and homotopy classes for the three-dimensional cobordisms, extending these maps. So a three-dimensional HQFT with target X is a symmetric monoidal functor. So what it does? So when we are given a three-dimensional cobordism whose boundary is this such a surface with a map and another surface in this case. Remember, in this case, when we apply z to this thing, what do we get? So on the objects we assign finite dimensional vector space. This is a finite dimensional complex vector space. This is another one, finite dimensional vector space. And this Bordism map assigns a C linear map. And in the particular case, if M, like this is closed oriented manifold, that means its boundary is empty, but the fact that this is a symmetric monoidal functor, and the monoidal structure on here is given by disjoint union and here tensoring over complex numbers. It implies that the empty manifolds, empty surfaces are mapped to complex vector space, complex numbers. So when we have closed oriented manifold with a map, then the associated invariant is an invariant of this map, which can be regarded as a number because such a linear map is determined by the image of 1. Because this is a linear map, and the image of 1 determines this linear map precisely. And that is the invariant that is associated in the HQFT. So remember, here I said output of an HQFT is a number to homotopy class of maps defined on closed-oriented manifolds. So this number is precisely this one. And the tree manifold equipped with a map or homotopy class has boundary. It gives some associated vectors, some linear map between the vector space on the boundary maps. But if it is closed, it gives a number. So I told you this category is way larger than usual cobordism category. How? You may say how? Because if we take any object, okay, we can embed in here by just constant homotopy class. Constant map, and then if we have any Bordism between things, then again we can equip with constant homotopy class. So we can in fact embed the usual cobordism category to this X cobordism category by adding this data of a map just using constant maps. No information about the maps. That's the kind of an inclusion. From this point of view, HQFTs can be regarded as extensions of TQFTs. So every HQFT, right? There's an HQFT, a symmetric monoidal functor from this category to this one. So every HQFT gives a TQFT by this composition. This is a TQFT. A symmetric monoidal functor from cobordism category to vectors. So from this regard, as I said before, HQFTs, homotopy constant field theories, can be regarded as extensions of TQFTs. This is yes. Say, so what has been done in this field? In the two-dimensional TQFTs are known to be classified by commutative Frobenius algebras. So when we choose the target to be BG, okay, in this case, G doesn't have to be finite. And G is just a discrete group. It doesn't have to be abelian. It doesn't have to be finite. Two-dimensional HQFTs with BG targets, classifying space of a group G, they're classified by what is called G-crossed Frobenius algebras. So in the algebra side is the same way. This G-crossed Frobenius algebra is an extension, G-graded extension of a commutative Frobenius algebra. And Tribe and Virelizier, this is a two-dimensional result. In three-dimension, Tribe and Virelizier, they extended the three-dimensional states on TQFT, okay, to HQFT with three-dimensional HQFT with target BG. Okay. And any spherical G fusion category, in this case, give rise to a three-dimensional state sum G HQFT. Okay. Again, this is this algebraic notion is parallel to two dimension. This is a G-graded extension of a fusion category. In the case of TQFT, 3D TQFT with state sum construction, then the Barrett tri-Vero Barrett Raspberry TQFT, what is the result is a spherical fusion category. For any spherical fusion category, they give a three-dimensional TQFT. So there is an extension of this theory to to three-dimensional HQFTs with BG targets. That's what I wanted to say. So let's see what is this object, G-graded extension of a fusion category. What is this spherical G fusion category, in particular G fusion category? It is a G-graded category. So that means every object can be written as a direct sum of these elements, these homogeneous elements which lie in the components. And if we pick two elements in different components, then there is no morphisms. So these components have no relationship between each other. And the tensor product of this monoidal category, this tensor category, behaves in the components, behaves like product. If we pick a homogeneous element in one, a homogeneous element in another, and then we take the tensor product, and it lies in CGH. And the identity component is fusion because it's an extension of a fusion category. So there's an embedding of a fusion inside. That is the identity component, and the unit object is fusion. And each component has finite many simple objects. So, but number of components doesn't have to be infinite. If G is infinite, then there are infinite many components. And then when G is not finite, C underlying category, the C is not fusion, but it is G fusion. That's a little bit remark. So I told you at the beginning, the motivation was like, can we get these invariants of associate, like the summand of a digraphitan TQFT as a more refined theory, as an HQFT, it's an invariant of summand. And here is the category that will get this. So we fix a group. It's just a discrete group. It can be finite or like in let's consider finite in this case. It doesn't have to be in general. And we take a three-core cycle. The objects of this category are elements of G, and morphism between the same components, just C, one-dimensional complex vector space. And as said here, if components are different, then it's zero. Here G is not equal H. And the tensor product of elements in here, and we have an associator. Associator is given in this category, is given by this three-core cycle. Then this invariant that Tribe and VLZ built is precisely pulling back this co-cycle and evaluating at the fundamental class. So this answers precisely that this HQFT with BG target from the state sum construction, one can get the components of this digraph written. So in particular, this is a refinement of this invariant. If we take a three manifold and we take this homotopy class, we associated this number. This number can be in a chosen specific category. It's just one of the examples in here. In a chosen nice simple category, then we can get this piece of the digraph written. So there's actually perpendicular generalization of this theory, like instead of from the point of view of homotopy types. So let's review some knowledge on homotopy types. So in topology, what we do, we take a topological space. One of the first things we learn in algebraic topology is the homotopy groups of a topological space, which are precise homotopy classes of maps from spheres to a fixed space. So that means for each topological space, we associate natural number worth of groups. Except only this one is set, rest is group. And we call the topological space X and homotopy N type if all of the homotopy groups above N vanishes. So from now on, they all become 0. We only have finitely many information, homotopy information. Such spaces are called homotopy N type. Okay? And one question in this combinatorial topology, combinatorial algebraic topology, can we find algebraic models for these homotopy N types? And then the first step is, can we do this for the 0 types? So what does a 0 type means? All homotopy groups in here is 0, and this thing is just number of connected components. So it's just for connected 0 type, it's just a contractible space, nothing else, just a singleton. That easy. For 1 types, okay, the statement is groups are algebraic models for connected 1 types. So for 1 types, we have everything from now on are just 0. We have pi 0 and pi 1. And once we say connected, this is also singleton. It's a singleton. So we have only one group. And in fact, this group determines the homotopy type precisely. So groups and connected 1 types are related like this. We take a group, associate a classifying space. This is functorial. And when we take a connected 1 type, we associate a pi 1 at a certain base point, which is a group. This is equivalence of categories. So next thing is the 2 types. In the case of 2 types, everything from here are 0, and we consider connected 2 types for simplicity. So this is also singleton. So we have 2 groups. Okay. And the cross modules are algebraic models for connected 2 types. So what is a cross module? Is a group homomorphism where the second group acts on the first and acts on itself by conjugation. And this map is H equivariant. So this is an action of H on E. And the second one is it acts on itself by conjugation. So it's an H equivariant. And the second one is satisfying this P-per identity. But don't confuse yourself with saying that this is E and this is H. This is not the case. The relationship between these are given as follows. We take a cross module. There's a classifying space. But the pi 2 of this classifying space is kernel of chi. And pi 1 of this classifying space is the co-kernel of chi. Okay? Not these groups, but pi 2 is the kernel in here. It's a subgroup in here. And H is co-kernel of this group homomorphism. So that's the relationship between cross modules and 2 types. Okay? A similar way, when we take a connected 2 type, we derive a cross module, associated cross module. And these are equals of categories. And examples like is for any group, this is a cross module. Because remember, if you have a 1 type, the rest of them are just 0. So this implies 1 type is a 2 type. So in fact, 2 types is a 3 type and 2 types is a 5 type because it already satisfies the condition to be a higher type. So this is in fact an embedding of groups to cross modules. Algebraically, you can embed 1 type to 2 types. And you can so topologically, you can embed the fact that 1 type is a 2 type, and like you can embed them. And this is the algebraic formulation. Any group is a cross module in this way. And this is similarly for simply connected 2 types. Yes. And for any normal subgroup, we have the inclusion is a cross module. And for any CW complex, we derive a cross module. So from this point of view, there are tons of examples of cross modules. Because for any topological space, for any CW complex, one can get a cross modules. So now I want to draw attention from the work. Like we go from groups to cross modules. It's like going from 1 types to 2 types in topology. And remember, for groups, we associated like digraphiton associate numerical invariants, right? For finite groups, digraphiton. So one may ask, is there a similar thing in the 2 type work? And Yetter asked this question and he answered. from a finite cross module, yet they derive yet they're invariant of manifolds. So what does a finite cross module means? That means both groups are finite. In particular, pi1 and like in particular, pi1 and pi2 of the corresponding 2 type is finite. Okay. And any Yetter's theorem is any finite cross module gives rise to a 3-dimensional DQFT. And how is the construction? Construction is very similar. We pick a base point and we choose a triangulation. We choose a total order on the set of vertices, and we put these labels. Okay, remember, chi is e to h. Now we label, okay, the chi coloring. Okay, I'm talking. We choose a total on the base, and then we define the chi coloring of the triangulation. So what does chi coloring? Remember, in the case of, if it's a generalization of digraph-Witten, this is the like digraph-Witten case. So we label in the digraph-Witten, remember, the edges of triangles by elements of G in a compatible way with the order, right? That's what I explained at the beginning. So this should be compatible with that, but more generalization. So in this case, so we again label edges with elements of H. Oops. In this case, we label elements with edges with elements of H, and we label triangles with elements of E. And this E precisely measure between this change between these two. If we go from here to here, we get H1, H2. But this is a relative pi2. This is precisely its boundary is a map from it's like a two morphism in a category. Let's measure this. Okay. Before we didn't have this because this was 1. Now we add more structure like pi2 elements, relative pi2 elements, and it captures precisely this way. Okay? It's really the extension of this theory, this digraph-Witten topology as well. So when we have a tetrahedra, we do the similar things on each faces. Okay, we color, we label color edges by elements of H, second group. We color triangles with elements of the first group, and in a compatible way with ordering. Okay, like we have total order on the boundary. When we go this way, we get an element of H, but we get this second element in here is given by the color of the each color of the triangle and the product of the first 2 edges. And these are given by everything compatible with respect to orientation. And in this case, we have 4 E labels, E, K, F, and L. In this case, they need to satisfy this condition. Because their boundary is, remember, there's a tetrahedra. Okay, that's why I put it, there's a tetrahedra. So it's homeomorphic to D3, okay, whose boundary is S2. So this is an element, this whole thing on the boundary, this is a condition on the boundary, right? Multiplication of elements in E. This is a condition on the boundary. When you multiply them with some action, of course, when you multiply these things, okay, this is a pi2 element because the boundary of this thing, tetrahedra, is S2. Okay, so this is precisely a pi2 element, but this pi2 element must vanish because this S2 bounds a disk because this tetrahedra is filled. It's a 3-dimensional object, and that's why we had this condition. So this is similarly, we do coloring, and then we count all chi colorings. Okay. One counts all chi colorings, which is finite because E and H are finite. Because we start with finite the cross modules, and then manifold is compact. So there are finitely many edges and triangles and stuff, so it's kind of finite. And then we normalize. And this is the Yetter invariant associated to finite cross module. So a really nice theorem of Faria-Martins and Porter. They wrote this map just as in the second map in the digraph-Witten. Remember, second formulation of digraph-Witten is overall all homotopy classes by pulling back the cocycle and then evaluating at the fundamental class. In this case, they formulate it in this way. Here, this is the space of continuous maps from M to B pi. And this is the base point. This is pi 0 of the space. This homotopy classes is pi 0 of the space. And then they also extend this to 3 cocycle, twisted version of it. And it's precisely pulling back this 3 cocycle to M, evaluating at the orientation is the fundamental class. So they reformulated Yetter's invariant and then describe its twisted version. With Alexis Virelizier, our work, like I told you, Troyev and Virelizier, they extended the G HQFTs in 3 dimension. The TQFTs, G HQFTs, which is a 1 type. So we asked the question, similar question, can we extend this TQFT to 2 type case, or GHQFT to 2 type case? And then we come up with this as expected chi-fusion category. Whenever we have a chi-fusion category, we are able to write, we can construct a 3-dimensional state sum HQFT with target this 2 type target. This is connected 2 type. And what is this chi-fusion category? Remember, when we are given a cross module. So as before, the group corresponds. So everything should be parallel. We are extending from 0 types to 1 types to 2 types. So in the case of groups, it should reduce the G-graded fusion category, G fusion category. So remember there we have graded objects. Okay? So on the level of objects, we should grade them by H. Okay? The objects are graded by H, but now we have extra grading on the morphisms. So morphisms are graded by this group E, and this relationship between objects and morphism by source and target maps, right? When we have a map between 2 things, which they say this is a component, this has this H degree this, Y has H degree this, and they are related by the cross module value of the degree of the morphism. So a degree of the morphism is in E, so its grading is in H. So this is the compatibility condition. In the previous case, there was no, remember in the G case, when we take 2 morphisms, X and Y was empty, was 0 when X is not equal to Y. But this is not the case anymore. X and Y in a chi-graded category may have different H gradings, but if these H gradings are related by some element of E, by the image of E under chi, then there may be a morphism between. So there's more connections between these 2, and it captures more of a topological idea. Okay? And we define simple objects in this way. And one of the main examples that we have is the example of this category coming from linearization of the stick-2 group. Objects are elements of H, and morphisms are linearizations of those elements in E, which are whose map, this is precisely, this can be called as E is in E, such that chi E H1 is H2. Right? This can be related like this. It's a linearization of this thing. How many elements we have such elements, and then we take previously generated complex vector space from these elements. Okay? And the remarks are when E is 1, it reduces H fusion category as expected. And when the kernel of the cross module is non-trivial, it's another fusion category because endomorphisms are never in 1. And restriction to 1 graded morphism yields H graded category. So we can forget this non-trivial graded morphisms and we get an H graded category again. And another restriction gives a fusion category. So since it's an extension, so we can do a lot of restriction to recover what is known before. In the case of fusion categories, what do we know? Finite dimension simple Hopf algebras and their representation categories give rise to the fusion category. So, and in this case, we ask a similar question. For these type of things, is there some algebraic object whose representation category is yields this chi-fusion category? And the answer is what is called Hopf cross-module coalgebras. And Hopf cross-module coalgebras yield whose module categories is chi-fusion categories. So what is a Hopf chi coalgebra? Is a Hopf H coalgebra plus a chi action. So next I will define them quickly. What is an Hopf H coalgebra? Is a family of C algebras equipped with algebra homomorphisms. Okay, we have algebras. Better I say AX. X is in H. We have algebras AX indexed by elements of H. Okay? And a family of algebra homomorphisms which are denoted like this. I'm reading from bottom to top. They're graded comultiplications and an algebra homomorphism co-unit and the C-linear isomorphism graded antibody. Okay, and they need to satisfy this generalized co-associativity, co-unitality, like graded co-associated, graded co-unitality, and the usual antipode axiom, graded antipode axiom, as expected in the usual Hopf algebra formula definition. A chi action of an Hopf algebra is okay. Remember, we have two pieces for Hopf chi algebra. This is the first step. And the next step is a chi action. It's an algebra isomorphisms, a family of algebra isomorphisms, which we denote like this way. We put E and it goes from AX to a chi EX, EXE. And that's the symbol we again read from bottom to top. And they need to satisfy this condition which comes from the notion of cross module. Identity, like element of 1 in E, act as identity. So when we compose two things, they act as group composition, like homomorphism property, stuff like that. So, and lastly, for finite dimensional involutive of algebra, there is an invariant of homotopy classes extended the Kuperberg invariant. So this is again numerical invariant. And involutory means as X composed as X inverse is always identity. So when you apply each involutory means when you apply the antipode twice with compatible boundaries, you get identity. From such an Hopf algebra, graded Hopf algebra with certain isomorphism symmetries, we get an invariant of this homotopy class of maps. And when the homotopy class is constant, it recovers the Kuperberg invariant of underlying three manifolds. It's the same scheme. We extend some TQFT invariants to homotopy classes. When the homotopy class is constant, then it recovers the underlying topological TQFT invariants of the manifolds. And how do we do this? We use as Kuperberg, we use the not state sum or triangulation formulation, but we use the Heegard diagram representation of three manifolds as a combinatorial way. And the first thing we should do, we need to encode this homotopy class into this diagram into this combinatorial representation of three manifold. Remember, in the case of state sum, right? In the case of state sum, we are able to encode. We were encoding the homotopy class by labeling edges and triangles in a nice way, in a topologically compatible way. That's one way of doing this. One way of putting the information of this coloring. And here is little maybe more subtle to see, but we can still do that. And how do we do that? The Hilgard diagram is a triple sigma, the Hilgard surface, upper collection of upper disjoint, pairwise disjoint simple closed curve, upper curves we call, and similar disjoint, pairwise disjoint simple closed curves, lower curves. Like in this case, red ones can be regarded as upper curve, and blue ones can be regarded as lower curve. Okay? And we encode the homotopy class, the idea of this map, f, and we are given f from m, maybe just the homotopy class. Okay, we need to encode this homotopy class of a map into this diagram. And how do we do this? We assign each upper circle an element of the second group H, and each lower circle, blue one, okay, an element of the first group of the cross module. Remember here, I keep using the same cross module. Okay, and they need to satisfy two conditions. Okay? And one of the conditions, I can say it's not that bad. When we have this, when we start from this lower curve, okay, on each intersection we have color of this thing. So we assign, let's say, chi lower one. Okay, so the first condition is beta of lower one. This is the lower one curve. This is the lower one curve. Okay, and we pick lower curves with the pointed. And if we take its cross module homomorphism, this must be equal to this alpha u1, okay, plus minus. And when we start from here and we look at intersections, we intersect with u1, so we put this one. And next we intersect with u2, and we put alpha u2 plus minus. And next we intersect with u3, we put alpha u3 plus minus. And next we intersect with u2 again, alpha u2 minus plus. And next, before coming back, we intersect again with alpha 1, so alpha u1 plus minus. And this plus minuses are just intersect how the intersection compatible with intersection. Like there's a way of to put compatible with the orientation of the surface or not. If it is compatible, the intersection, then you put plus, or if it is not compatible, it's minus. So this is one of the conditions. And this is precisely the condition that it's a disk, this lower curve maps to a disk on B chi, and its base point, this base point goes here, okay? And this whole thing on the boundary, I draw better maybe blue. This is beta L1. This is some relative pi 2 element in B chi, but it bounds, okay? So it's a disk because it bounds on the lower handle body. Okay, there's a disk that bounding it. That's why it's a trivial when we look at its boundary. Its boundary consists of this intersection. First it goes alpha 1, alpha 2, or and we do this, so it bounds. So this is the condition. There's a lot of topology inside, in fact. Two-dimensional topology of two complexes and things relative pi 2, boundary mapping. And the point is, this is a chi labeling, and we define also equivalences of chi labelings because this encodes the data of a map, okay? Not a homotopy class. So when two maps are homotopic, they should give equivalent like chi-labelings. So this is algebraically, we define gauge equivalences between chi-labelings. So number of chi-labelings of a Heegard diagram of a three-manifold up to this equivalence relation given by gauge equivalences are in correspondence with the homotopy class of maps. This is the crucial point of this building of this invariance, always. This is homotopy classification theorem. On left-hand side is precisely topological, just number of homotopy classes from close-oriented three-manifold to two-type, connected homotopy two-type. And the right-hand side is just certain algebraic maps satisfying certain conditions up to algebraic equations. It is really algebraic description of this homotopy class of maps. Okay? And to define invariance, we need to have integrals and chi-integrals. So I will not go over this. They're a little bit technical, but integral is an element of the identity component of this Hopf-Chi coalgebra. And chi-integral is a collection of linear forms on other components that satisfy certain conditions. But the point is, under some normalization condition, there is a unique chi-integral and then a two-sided integral satisfying this normalization condition. But these integrals and things, they're a little bit technical and whatever, but we use them. So, okay, well, how do we construct this invariant? How do we construct this KAF invariant? This is of Chi coalgebra. This is a homotopy class. Okay, and this is the invariant of this homotopy class, which is just complex number, constant. Okay, how do we do? We choose a pointed oriented Heegard diagram as we did above. So this is precisely sigma upper curve and lower curves. And we choose a chi-labeling encoding the homotopy class of this one. So F is just a homotopy class. We pick a representative of F. Okay. It's just, there's a choice involved. We choose a representative and then we look at its chi-labeling. And then we write down a graphical diagram using these labels. Okay. So what do? We start, we have a diagram like here. Okay? We have a diagram like here. At the bottom, we have lower circles and there's order between them. So we pick the first lower circle. Okay. We look at its E label. Then we put this E label as a chi action. This is these triangles. I go over fast, but they are integral elements. This is unique, and these are chi integrals. Okay, maybe I just go. If you look at these things are chi integrals, and these things are integrals. So integrals are on the bottom always. Just there are number of integrals elements is number of lower circles. Number of chi integral elements are number of upper circles. And we start from the bottom with integral elements for each lower circle, and we put the chi action according to the E grading of the lower circle. Okay? And then we apply co-multiplication, graded co-multiplication, according to the intersection of these lower circles with the upper circles. This is the first. When you follow this lower circle, this is the color of the upper circle. First upper circle that it intersects. This is the color of the second upper circle that intersects, and this is the last one. Okay? And we do this for each lower circle. The second lower circle, it has this label, we add this action, and then we apply this coproduct. The order going from left to right is precisely the order when you follow this lower circle from starting point and following its orientation. Okay? Of course, and these boxes are precisely encoding the intersection points. If intersection point is positively signed, okay, remember I wrote it at the here, there is positive and negatives. And like this is precisely how do we write these things. Okay, this is the first one, this is the second one, this is the third one, like this. And if the intersection point is positive, this box is identity. If the intersection point is negative, this box is antibode, SX, SH2. Okay? That's how do we fill these boxes. If the intersection point with upper and lower circle at this intersection, we put if it is positive identity, if it is negative intersection, we put antipode, which changes the color with its inverse. And then we have if you look at how many strands are there here, the number of strands here is precisely number of intersection points with upper circles and lower circles. But if we go from here, we count them by picking lower circles, like picking the first lower circle and following intersection with all other ones, picking second lower circle, intersection over all other ones. And one can do the other way around. One can pick an upper circle and then follow intersections on that upper circle. Okay? They're all colored with this upper circle. And again, similarly, one can follow the next upper circle and how many intersections with this lower circles. Okay? So there's a number of intersection points can be counted two ways. If you can fix the upper circles first and then count intersection points each upper circle. This is the top part. Or you can fix the lower circles first and then count the intersections of the intersections for each lower circle with upper circle. And this is this part. So there's a unique the symmetric group element on the number of intersections of upper circles and lower circles that relates these intersections, these strands. And this box is precisely there's an element of this number of intersections on the symmetric group. And then we apply the multiplication in the graded Hopf algebra, and we apply the chi integrals. Okay, this is not the invariant. When we do this, if you are familiar with the graphical calculus, this is precisely a diagram from C to C. Okay, it starts from the empty set to empty set. So it goes from C, it goes to HA for something in Hopf algebra. It applies another thing, A. It applies symmetry, and then at the end it begins to C, which is a linear map. It corresponds to a number. Well, in fact, these are elements. It's immediately a number, and we normalize this number with this normalization factor. Okay, that's the last step. And the claim is this is invariant of the choice of Heegard diagram, the choice of chi labeling of this representative of F, and plus what else? Yes, it's independent of the homotopy class of this F. One can do another representative. It's independent of all of the choices that we have made. Okay, and one thing is if F is homotopic to constant map, so homotopy class of the constant map, this associated, the invariant is the Kuperberg's original invariant of the underlying involutor of algebra. So it's grade 1. It's like A1 of X in H, AX, grade algebra. And we show that this invariant is not trivial one. In fact, it can distinguish what is called phantom maps. So it is stronger than the pi map. So what is two maps like F from M to B chi is phantom if pi 0 F, pi 1 F, pi 2 F, right? They are pi I M to pi I B chi for each of them are all 0. So if this is the case, it does not imply that F is constant. Okay. If F is constant, this is always true. Yeah, constant map induces 0 map on homotopy groups, but there are certain maps which induces 0 maps on homotopy groups, but they are not homotopy constant maps. These are called phantom maps. Like they're phantom with respect to this homotopy group phantom. But we show that this invariant can distinguish a constant map from some other phantom maps. In particular, it is stronger than this homotopy counter, PIs, PIs. And the last thing is this invariance can be interpreted as the invariance of the principal two bundles over this three manifold. So this is can be interpreted as homotopy classes in here are principal two bundles over M. So since for each element here can be corresponds to some principal two bundle over M, this invariant associated with this homotopy classes can be interpreted as invariants of such geometric structures for them. And in fact, yeah, this is my slide, and thank you for your attention. I'm a little bit over time, I guess, yeah.
Okay, thank you for your talk. Very beautiful. Is there any questions or comments? Okay, I have a question.
Mhm.
So at the beginning of your talk, we considering the closed manifold. So actually, I'm very curious about how about the manifold with boundary. You
Oh, I
know,
see. Uh-huh.
you know, because for not because we are interested in the knot theory, and
Mhm.
most of time we curious we interested the complement space of a knot.
Yes.
So I think about according your talk, I think it may very associates with the north not invariant, but I'm not sure which invariant is very associate. Mm, maybe Higard floor homology, or maybe uh, the not group. I don't know. So
Mhm. Mhm.
how do you think? How do you think?
Yes.
Thank you.
Now this theorem, this is in fact the state sum, not the Kuperberg. This thing that we built is in like TQFT style, so it associates something to manifolds with boundary, some vector space. But this vector space encodes this again the homotopy class of this map. So this is more. These invariants are more of an extension of quantum invariants like TQFTs. Yeah, he got Fuller homologies also can be regarded as 3+1 TQFT. I don't know, do they have any connection? It says he got Fuller is more involved in terms of construction. And these are 2+1 TQFTs, and that's a 3+1 TQFT. And in terms of knots, our next project is like there is Reshedekin triad TQFT or surgery TQFT,
Yeah.
and they associate invariants of again three manifolds, but also invariants of three manifolds with three manifolds with a knot inside. So, and then these TQFTs are also extended by trivial
Oh, Taurus.
to 3D HQFTs with BG targets. And we are we want to do this to B chi targets. So in that case, when we have a three-dimensional manifold with a knot inside and a homotopy class of map from this triple, then we expect to some associate invariance that extends these two constructions, some numerical invariant to those things. So the three manifold can be S3 and the nut inside, and then map from the complement of nut to this 2 type. Then there may be we can associate an invariant. But the connection, I don't know of a connection between these theories and other well-known studied EQFTs.
Okay, thank you very much.
Yeah, you're welcome. Thank you so much for the question.
So if there are no other questions and comments, let's thank you and welcome our speaker, and maybe see you next time. Thank you.
Thank you. Thank you so much.